Linux is the one that we'll be concentrating on here since it's available. But you can take a look at that. We've already explained most of that. Recall that the Verilog Messages holds a system messages log, and so that may be of some interest too. If we want to take a look at Verilog Messages, it holds a lot of the system logs, and it gives you the time and then the message associated with it. And we can move down here and notice it tells us information about various services and about various things that have occurred during the running of the operating system and during the boot time and reboot. And so sometime you might want to go through here and search for the word error to determine if there's anything going on that shouldn't be going on. So we search for error or fail. Okay, let's add inodes. There we go. Okay, a couple of Linux file systems. One of the earlier ones was called EXT, which is the extended file system for Linux. And a few years after that, they came out with more robust file systems, one of which was called the EXT2 file system, the second extended file system. And later after that, an even more robust file system called the EXT3 file system, which actually include journaling after that. If you recall our discussions about NTFS, which kept track of the transactions that occurred, essentially this is the same thing that occurs here, is that there's a journaling version, EXT3, that actually keeps track of the transactions that go on. So if the file system is ever, or if the operating system ever crashes, then it can go back, instead of doing a complete check of the file system, which takes a long time, for example, under the EXT2 file system, the operating system could just look at the journal and see what transactions had not been committed. It could go back and actually fix everything that was a problem. Under EXT2 and EXT3, it employs something called inodes, which are pointers to other nodes. Inodes are blocks, and essentially an inode holds information about a block in files on the file system. And so the file system keeps an internal link count of everything that's being used. And so an inode, if it's being used, it will, and a blocker is being used, and there will be a count of the number of blocks that are associated with the inode. And once you delete all the files, the inode for that file count value is set to 0, indicating that that inode and the blocks associated with it are no longer being used. And the Linux file structure holds metadata and data, the information about the files, which are represented by inodes, holds metadata, and then of course the inodes will hold information about where the data associated with those inodes is located, as we'll see here shortly, hopefully. Here we go. And so if just a graphical representation of the EXT file system is here we have an inode, which is usually is a 1024-bit of size of information about a file, and this inode will hold pointers to the data blocks associated with the file. So this inode would indicate that it's got 3 data blocks associated with this file. And so recall with NTFS is that files are not represented by their file names, they're actually represented by a distinct number, a unique number, because you can have the same file name hundreds or thousands of times throughout a file system, but you want those files to be distinct. And so an inode number is what is used to represent a file. So if we go in and we want to look at the inode numbers associated with each of these file names, we type a -i, and this tells you all the unique inode numbers associated with these files. And so these are just the inode numbers. So recall that everything is a file under Linux, and files are defined as objects which have attributes, and each of these attributes has values. And Unix file systems consist of 4 components. It has a boot block, a disk allocation unit of at least 512 bytes that contains the bootstrap code, and that's going to be in the first 512 bytes of the file system, and there's only a single one of those. And so in that sense, it's similar to the master boot record on a NTFS. It also contains a super block, which has a disk geometry. It shows available space on the disk and the location of the first inode. And later on we'll see, we'll do that in just a second. And this is used to manage the file system. So after that comes the inode blocks, which is the first data right after the super block, and it assigned to every file allocation unit. And then we have data blocks. So let's go back in here. If you recall what, let's go back here and see what we've got. So if we run FSTag-F, first of all, let's do a file on assignment 2 to see what type of a file system it is. It says it's Linux revision 1 ext2 file system data. Okay, so now we can go back and run FSTag from sleuthkit with F equals ext and the name of the file. And this gives us all that information, including the location of the super blocks and inodes. There we go. Okay, the file system information, it says that the file system is ext2. It doesn't have a volume name. It has a volume ID of this hex number. When it was last written, when it was last checked, and by checked that means that the file system checked when that was last checked to make sure that the file system was clean, and the last time it was mounted. Let me see. The source OS is Linux, and this gives you the metadata information down here. The range of inodes ranges from 1 to 1024. Root directory, there's 2 files within the root directory, and the number of free inodes is 1012. So it tells you how many inodes are being used. That doesn't necessarily mean that there's a number of files on here, though. Content information, the block ranges run from 0 to 4095 and the block size of 1024, which means that there's 2 sectors per block on this file system. The number of free blocks is this, so this is the amount of free space associated with this file system. And the number of block group information, the number of block groups is 1, and we'll see what this is shortly. Number of inodes located in these groups is 1024. Number of blocks per group is 8192. Noticing number of block groups, there's only a single one, and it starts with group 0. It says the inode range, the block range, which is consistent with what we saw up here. Notice that the super block is going to take up 1 on this operating system, because it's this file system, because this is a very small file system. In fact, let's see how large this file is. It's only 4 megs, and so we only need 1 super block. The data bitmap indicates which sectors are being used. The inode bitmap. The inode table runs from starting at block 20 and runs through block 147, and the data blocks run from block 148 right after the inode table all the way to 4095. And so this is the actual data area. This indicates the number of free inodes, the percentage, number of free blocks, 93%, and the total directories in here are 2. And so that gives you a lot of information about your image running FSSstat. FSSstat, yes, that's right. Okay, the inodes, again, point to a specific physical location on a drive. When a file is saved, an inode is assigned that data blocks of 4096 or 8192 blocks are clustered together, and that depends on the file system. Typically for larger hard drives it's going to be 4096. However, as you see for this small image, which is only 4 megabytes, you don't need such large blocks, and so it only created block sizes of 1024, which once again are going to be 2 sectors. And I'll leave this for a second because it needs to be explained first. So a bad block inode keeps tracks of disk's bad sectors. Where did we see this on the FAT system? Where was this located? The bad blocks are located in the FAT. And where are they located in NTFS? In the bitmap section. And if you want to try to recover information on the bad blocks, you can use any of these command line utilities. Bad blocks, mke to fs, and e2 fs check. Okay, we already know that. Let's go on down here. And okay, now getting more specific information about the command structures. We have two primary control structures at the beginning of the file system. Once again, we have the super block, which indicates the type of file system, its size, the number of data blocks, the number of free inodes, the free space available, and where the inode table is. Let's go right back here. And we see all of this is being read from where? All this information is being read from the super block, correct? And for redundancy's sake, on an EX2 and 3 file system, their copies of the super block are stored at regular intervals in case the original gets trashed, and for efficiency purposes. For this small one, there was only a single super block, as was mentioned earlier. Okay, inodes once again keep tracks of the file types, the permissions, the number of links, the owner and group, the size of the file, and when it was last modified, accessed, and created. And we go here, and so if we run, let me see, let's look at the files that are on this file system. There we go. So there's 2 on there. Notice that lost plus found is a directory. Didn't say it had two directories, I believe. One would be the root directory, and this is the other directory. And then we have this file right here, which is inode 12, which is the file recover. And so if we run istat on that, we can see this gives us the information. This is just reading the information about inode 12. Notice it says it's allocated. It belongs to group 0. I'm not sure what that means. UID and GID of 0 and 0. It shows us the modes. It shows us the size of the file, the number of links, the inode times. The file was last accessed at this time, last modified here. And this is inode modified. What would that be? That would be the change time. So those MAC times, that's a change time. So anytime a piece of the inode is modified, it would be reflected in here. And then we see something called direct blocks. And we'll see what this means in a second. But if you recall what run lists are in NTFS, it indicates the blocks that comprise the file. And these indicate the blocks that comprise the files right here. And so these are all the blocks that comprise the files. And you may think these are contiguous, but they're not. And we'll see why that's so in just a moment. But you'll see here down here there's something called 2573. The indirect block, this is actually going to be a block that consists of inodes that point to some other blocks located in these data blocks. So if we go up here and look for 2573, and here we'll see it's skipped. Notice that 2571, 2572, 2573 should be here, but it's not. But it starts up again at 2574 and on down. And we'll see why that is in just a moment. But we'll see that from 2561 to 2571 is 11 blocks. Then we have an indirect block. Well, let's see why that's so. Well, each inode has 15 pointers to the actual data on the hard disk. And remember, these are pointers. They are not actual data. So they're like the run lists that you find in the master file table for files. So each of the 15 pointers to the data is a block address on the hard disk. And what are these? These are block addresses. These are actually physical block addresses. So 2561 is the 2560 second block, because it should start at 0, I believe. 25 second block, physical block on the hard drive. And this is how this works, because if for each inode here we have an inode pointer, and so each inode will have this many pointers that point to the blocks that are located here. Notice that 01 pointer points to block 1, 02 block pointer block 2, on down here to 10. And so this indicates that these blocks are associated with this file. But if this were the case, then if we were to include all the rest of the pointers down here, you would only have a limited amount of information that could be included in a block, enough for just 15 pointers. So 15, I'm not sure why it stops at 13. I think it was because it would fit on this graph. So block 15, you would specify the block size times 15, and that would give you the total size maximum that a file could be composed of. So in order to create larger files, what we've done is that for these remaining 3 pointers down here actually point to indirect blocks, which are just like these blocks, but instead of containing data, they contain pointers to other blocks. Once again, this is going to be data. This is a pointer to an array of pointers, of 128 pointers. And each of these can point to a block. So this array of 128 pointers points to block 11, 12, 13, 14, so on down to 138. That still gives you a limited file size that can contain on a file system. So in order to create even greater files, larger files, we have another pointer which points to 128 pointers. That is an array of pointers. However, those 128 pointers, each of those pointers points to another array of 128 pointers. So now we have 128 times 128 different data blocks that can be accessed. So each of these pointers ranges from data block 139 to 128 squared. And so now we're getting larger, we're capable of having larger and larger file sizes, but that's still not large enough. And so finally we have something called, notice that this was called an indirect block, because these were directly pointed to by this inode. This is an indirect block right here, because we have a pointer to a pointer, then to the block. Here we have a double indirect block, because this pointer points to this array of pointers, which points to this array of pointers, which then points to the data blocks. And finally, on the very last pointer is called triple indirect blocks. And so this pointer points to an array of 128 pointers, which each of these pointers points to 128 pointers, and each of these pointers points to another array of 128 pointers. And now we have the capability of representing much greater file systems, all the way to here, the block 128 cubed. So for very large file systems, we'll have direct blocks, indirect blocks, doubly indirect blocks, and triply indirect blocks, which means we can have very large file sizes. But this is essentially what an inode does. It's pointers to the data blocks comprising a file on a file system. So here we see that, and boy, this will be very fragmented, as you see here. So these are the first. What are these going to be? These are going to be the direct blocks. Wow, this is massively fragmented. And so this is pointing to the data right here. Notice 3145 is going to point to this. This is a direct block. Once we get down here, 567 is pointing to an inode here. And this inode here, notice this is 567, then has a pointer to this. This is an indirect block of data. And then on here, 5601 points to data block, a block 5601, which contains a pointer, 5151, which points to this block, which then points to the actual data block right here. And then we have triply indirect right here. Pointer in block 43, this is block 43, points to 1979 right here, which points to 988 right here, which points to 911, and 911 is going to be the data. Okay, each inode block is 1024 bytes, and therefore the maximum file size on a Linux file system is around 15K. That's only if we consider using the direct blocks. So if all 15 pointers point to 1024 bytes block, then you could only have a file up to 15K, and we've kind of already gone in this, so I'm not going to go into this too much further, but you can download this and read the notes, and this just indicates the fact that the first of 12 blocks actually point to data, and then the other 3 will actually be pointers to other pointers. The 13th pointer points to a block on the hard disk that contains the real pointers to the data. These are indirect blocks, and then doubly indirect blocks and triply indirect blocks. And so I'm going to go ahead and let you read this on your own. And this is just showing, once again, file system. And okay, let's move on down. And so if we want to get very large file sizes, what we can do is increase the block size not from 1024 but to 4K 4096, which means that then we can have files of the size 4 terabytes, which means we can also have file systems of that size. However, because the size field in the inode is a 32-bit value, we can only max out at 4 gigabytes. 2 to the 32nd is going to be 4 gigabytes. However, the file sizes can be 4 terabytes. And just another example of an ext2 inode. Notice that it contains information on the mode, read, write, execute, the owner information, their UID and GID, the size of the file, the timestamps, and then we have the 12 blocks right here, which are direct blocks. These are pointers to the data out here. Then we have the indirect blocks, which are, this is a pointer to a series of pointers, which then point to the data out here. Doubly indirect blocks right here. Notice that here's 2 right here. Here we have singly indirect, and then we have doubly indirect right here, which then points to the data, and then there's no representation down here of the triply indirect blocks. So specifically what an inode contains. The inode is the basic building block of the file system. Every file and directory in the file system is described by one and only one inode. So the ext inodes for each block group are kept in the inode table together with a bitmap that allows the system to keep track of the allocated and unallocated files, and just see simply about all the information about. If we want to use something called the stat command, the stat command actually goes in and reads the inode information. It tells us the file name, the file size, the number of blocks. Each block is 4096. It's a regular file. The device, the access controls, the permissions, that is, the UID, the GID information, the owner information, and the less access modified in change time. Oh, just so you know, right here, notice this says minus 0400. If you recall that that file times are represented on Linux systems by the number of seconds since the epoch, which was December 1st, 1970. And so depending upon the time zone, it's important to be able to represent the modified access and change time, because the time when the offset from the time zone will tell you the actual modified access and change times. And so this actually gives us the offset from Greenwich Mean Time, Universal Coordinated Time. And so in the Eastern Time Zone, it's going to be typically, when it's not Daylight Savings Time, it's going to be minus 0500. But since we're in Daylight Savings Time, we jumped ahead an hour. It's only going to be 0400. Okay, inode information. The mode holds 2 pieces of information. This inode describes the permissions that the users have to it. And it can, each inode can describe a file, a directory, a symbolic link, a block device, a character device, or a first in, first out device. It holds, if we want to see if that's the case, we can go back here and do an stat on dev HDA. So this is the hard drive, and so this is what this actually represents our hard drive. So notice that it tells us the file size, which is of size 0, because it's really only a file that is pointing to the physical device, number of blocks, and so on. And last time it was accessed, modified, and changed. We can do the same thing for the first partition as well. It gives us the size and file bytes. Okay, in the ext2 file system, directories are special files that are used to create and hold access paths to the files in the file system. A directory file is a list of directory entries, each one containing the following information: the inode for this directory entry, the name and length of the directory entry in bytes, the name of the directory entry. And so the first two entries for every directory are always the standard dot and dot entries, meaning this directory and the parent directory. It also holds timestamps, the MAC times, and it holds data blocks, pointers to the blocks that contain the data that this inode is describing. And let's go to this to talk one more time about the super block, just a little more information so you understand about the group descriptors. So recall that the super block contains a description of the basic size and shape of this file system. And how do we find that information? Using FSTag, right? So the information within the superblock allows the file system manager to use and maintain the file system. So usually only the superblock in block group 0 is read when the file system is mounted, but each block group contains a duplicate copy in case of file system corruption. So it also holds a magic number, which allows the mounting software to check that this is indeed the superblock of an ext2 system. It has a revision level, mount count and maximum mount count, and a block group number that holds the copy, this copy of the superblock. Contains information on the block size, which we saw before, and the blocks per group. And the blocks per group is a number of blocks in a group. Like the block size, this is fixed when the file system is created. It holds the number of free blocks, the free inodes as we saw, and the first inode. The first inode is the inode number of the first inode in the file system, and the first inode in the ext root file system would be the directory entry for the root directory. Now let's talk about the group descriptor. So each block group has a data structure describing it. And like the super block, all the group descriptors for all the block groups are duplicated in each block group in case of file system corruption. So each group descriptor contains information on the block's bitmap, which is the block number of the block allocation bitmap for this block group. So this is used during block allocation and deallocation. The inode bitmap, the block number of the inode allocation bitmap for this block group, which is used for allocation and deallocation, and the inode table. And also contains free block counts, free inode counts, and used directory counts. So essentially, each block group is going to consist of the super block and a block group descriptor. And so this should be down here like this. So the group descriptors are placed on after another, and together they make the group descriptor table. And each block's group contains the entire table of group descriptors after its copy of the super block. And only the first copy is actually used by the ext file system unless the block group 0 somehow is damaged, and then the other block groups can be used. And so the first inode we need is when the operating system boots is the inode for the root of the file system, and we find its number in the file system superblock. If we go back here and take a look at FSTag-F ext and assignment 2, notice it says number of block groups 1. The reason it only has 1 is because it's a small file system. It tells number of inodes per group and number of blocks per group, 8192. And the block range, it tells us the inode range and the block range. It tells us where the super block is located in the group descriptor table, the data bitmap, the inode bitmap, and the inode table, and the data blocks. All of this is contained in that first block group, which includes the super block. And going down here, okay, UNIX Flavors finally. The different UNIX flavors. People say that Unix is Unix, but that's not necessarily the case as we've seen thus far. Most of the commands you will see, I'd say, I'm guessing 70 to 80% are the same. However, the file systems are the same. or excuse me, the file systems are going to be similar, but they're not going to be same. The commands are going to be somewhat similar, but not exactly the same. These, from what I found, are much more similar than these. In other words, these are really flavors that are fairly similar to each other. I know they're not exactly the same, and these are fairly similar to each other, not exactly the same. The Linux distributions, remember Linux is a kernel. A distribution is just a set of utilities that is added to the kernel, and so on. So that ends this look at the ext2 file system. And what you need to do is to read Brian Carrier's book, starting with page in chapter 14 about chapter 14 about ext2 and 3, and then you'll have an assignment coming up shortly.